In this example, we've got a block on a frictiony table connected to the wall with a spring and connected to a hanging block by a rope over a frictionless ideal pulley. We're given the masses of the blocks, friction on the table, spring constant and initial length of the spring, and we need to find the spring length at its maximum stretch and at its maximum velocity. Also, what that maximum velocity is. So to start out, we will draw free body diagrams. We need one for each block. So here, for block A, we'll have the spring pulling to the left. We've got tension pulling to the right. We also know that the friction force is going to go against that motion. We have the weight going down, and we've got normal force going up. Now for B, we just have the weight going down and tension going up. We need to put some states in here. So let's say, okay, coordinate frame. Well, since unstretched length of the spring is 0, then we will just start that coordinate frame here. So we'll say y, x, and then say state 1 is here, and state 2, which is max velocity state, be here, and then state 3 is going to be max stretch, which will be a little further. That's here. So for the first part, find the length of the spring at the max stretch. We can use work and energy from states 1 to state 3. So 1 to 3, we know that energy at 1 plus work from 1 to 3 equals energy at 3. Potential energy at 1 plus kinetic energy at 1 plus work from 1 to 3 equals potential energy at 3 plus kinetic energy at 3. Now let's see what we can cross out. Well, we put our 0 up here at the top of the table. Say these blocks, say B starts at the top. Doesn't necessarily have to do that, but otherwise you would account for it, and then the places where you account for it end up canceling out with its initial thing, so we can just say it starts at the top. It'll be easier. So up here at start, no potential. Also, up here at the start, the blocks aren't moving, so there's no kinetic. Now here at the end, the spring is stretched and B has fallen, so there will be some potential energy there. But since they're stopped, they're not moving, there's no kinetic. So then basically we just have this work by friction equaling the change in potential energy of block B in the spring. So we put those in here. But first, actually, we need to find what is the friction force and check if the blocks actually move. So for B, we know that sum of the forces in the Y equals MB times A. So we have that MBG minus T, say A is going down, And then for A, sum of the forces in the y equals 0 because the block is not moving off of the table. So see, we have normal force going up, MAG going down, N equals MAG. So then if mu equals mu MAG, so we put numbers in here for static, then that equals 49 newtons. And for kinetic, that equals 19.6 newtons. So then sum of the forces in the X equals MA, which equals that tension minus the friction force. So we'll say K times L minus L naught from the spring minus this friction right here. Now for the static check, we need to see, is the weight of B big enough to overcome this friction force and make the blocks move? Well, at the very beginning, so to overcome the static friction, acceleration would be 0 and also the spring would not be stretched. So we need to see if the weight is bigger than the friction force. So compared to 0, we need to make sure that MVG is greater than static friction. So putting numbers in here, 15 times 9.81 is 147 minus 49, 98 is greater than 0. So the blocks slide. Well, good. So now we know that we can go back here to the energy equation and actually figure some stuff out. So putting numbers into here, we know that, well, let's see. We'll do the formulas first. So the work from 1 to 3 is the work by friction, but it will be the work by the dynamic friction. So negative FD, because it's sapping energy from the system, times the distance that they slide, which is X. And that equals the potential energy, which is however much B fell, minus MB times G times that falling distance, which also happens to be X, because the distance that A slides is the same as the distance that B falls. So we just call that X. And then we have to add that spring stretch, 1/2 K. And how much did the spring stretch? Well, stretched by X. Okay, so conveniently, we can cancel an X from here, from here, from here. And then we'll just have MBG minus FD equals 1/2 KX. So 2 times MBG minus FD over K equals X. So then if we put numbers in here, we get 2 times 147 minus, this is 19.6 over 100. X equals 2.55 meters. So this is the maximum stretch in the spring. We found A. Now, we need to find the spring length at maximum speed and then what that maximum speed is. So For this, we know we've got to find two things. We need at least two equations. So at the maximum speed, what can we say about the acceleration of the blocks? Well, it's got to be 0, because we have, say, the speed of the blocks starts at 0. Okay, so we've got v here. This is time. The blocks will start moving, get faster, and at some point they'll stop and start going the other direction. Now, because there's friction, then they won't go back quite as far. Boom, boom, boom. It'll be something kind of like that, except in this case, this will be x. So we need to figure out, well, at maximum speed, acceleration, which is the derivative of speed, has to be 0. Because if the acceleration were not 0, then v would be either increasing or decreasing. If acceleration is 0, then what is that speed going to be, and how much has the spring stretched? So from the free body diagram, then we know, so we'll go 1 to 2. We'll use Newton's method here. So at max v, acceleration equals 0. So we know from these force equations over here, from B, we know that 0 equals mb g minus t. And then for A, 0 equals t minus k x minus friction. So here, we can solve t equals mb g, and then we get 0 equals mbg minus kx minus ft. So we rearrange x equals mbg minus ft over k. We put numbers in here. X equals this 147 minus 19.6 over 100. So it's going to be actually half of the max stretch. This makes sense. Max velocity kind of in the middle of 0 and max stretch. And that is going to equal 127 1.27 meters. So this is x at max velocity. And then to get that max velocity, we'll use work and energy. So energy at 1 plus work 1 to 2 equals energy at 2. Now that we know what this x is, instead of solving for x like we did in the first equation, we'll be able to solve for v. So potential energy at 1 plus kinetic energy at 1 minus that friction work equals potential energy at 2 plus kinetic energy at 2. And remember, at 1, all the blocks started at 0, there was no potential, 0 velocity, no kinetic. Well, at say 2, they're going to have potential because B has fallen some and the spring has stretched. And then we'll have kinetic because A and B are both moving at max speed. So negative friction force times the distance equals negative mb times g times that distance plus spring energy 1/2 k x squared plus kinetic energy 1/2 ma plus mb, because they're both moving, v squared. So then we've got x times mbg minus fd, that's times 2, minus minus k x squared over ma plus mb equals v squared. So then if we put numbers into here, 2 times 1.27 times 147 minus 19.6 minus 100 times 1.27 squared, divide by 10 plus 15, all square rooted, equals 2.55 meters per second equals v. So velocity, this is the max speed. Then the spring length then is going to be half of the longest possible spring length. So to solve this problem, then we found free body diagrams, assigned coordinate frame, figured out if the blocks move by the static check. We wrote our force equations, our energy equations, solved out for the unknowns. Now, one interesting thing about this, we saw that velocity starts at 0, it increases, then it stops, then it goes back the other direction, forward, forward, forward. So it's sort of like constantly shrinking oscillation. So here, this means acceleration is not a constant. So there's no one single acceleration you could solve out for to figure out what is the position at every single point. So to do this, we'll actually have to solve it like a differential equation. Okay, so for A and B, from the force equations, we know that for B, we have MBA equals MBG minus T, and for A, we have MAA equals T minus K times L minus L initial minus friction force. Okay, this is for that forward sliding motion. Well, if we rearrange here, we get T equals MB times A minus G. Here T equals MAA minus K times L minus L initial minus dynamic friction. But we also know T equals T. So we can say MB A minus MB G equals MA A minus K L minus L initial minus FD, which if we actually put the formula for that, we'll have mu D MAG. But here, in order to solve this, we need everything in terms of x, that's stretching distance. So we have MB x double dot, acceleration is second derivative position, minus MB g equals MA x double dot minus KX minus mu D MAG. We'll get MBG equals MA plus MB x double dot plus KX minus mu MAG. But this is for the blocks sliding forward. What if once the blocks reach their max spring stretch, they'll start sliding backwards and friction will point the other direction. So really, this needs to be multiplied by a sine of the velocity. Now this here is a discontinuous differential equation. It has to be solved numerically. So if we look at sort of what a graphical representation of this would be, then first we can solve out for acceleration. So we know that mbg minus kx minus, plus ud mag times the sine of x dot equals ma plus mb x double dot. Or we can divide all that by this ma plus mb and get the x double dot. So to express this graphically, we can say we want x double dot, then we integrate to get x dot. We integrate again to get x. But to get x double dot, we had to divide by 1 over ma plus mb. And that has got to be all these other things kind of added together. So we have that mbg. So that goes in here, gets added. And then this velocity, we need to get the sine. We need to multiply that by the friction force, mu mag. We need to subtract it. And then we have to add in the spring. So this gets multiplied by k. And that's also subtracted. So this is a graphical representation of what the system looks like. And then, so I put it in here, Simulink. This is a MATLAB thing, and you can use it as a numerical solver. So then I wrote a code, which we'll see here. I have the masses of the blocks, static and dynamic friction, gravity, spring constant, spring length. And so if I run it, we'll see what happens to the blocks. So that green is the spring, and then the blocks are the pink and the blue. You can see that they bounce some, and then they kind of come to rest. Now here, we can see acceleration is changing. So acceleration is this red line. So it starts out high, it crosses 0. Where it crosses 0 here is at that max speed. Speed is the blue. Does that make sense? So it goes all the way here till max stretch, which you can see is that maximum position. And then acceleration flips and it starts moving in the other direction. So then velocity is negative, position is decreasing. Now because of that friction, it doesn't go quite all the way back to where it started. You can see the speed is also kind of lower. And then eventually it just kind of evens out. Now we can see that will change a little bit if, say, friction is even lower. What if friction is 0.1? We'll run it and watch what happens. So you can see with less friction, it bounces a lot more. So you can see here that it's a lot smoother and there's more bouncing. And then let's say we put this back to 0.2. And what if we made B a lot bigger? What happens then? Say B is 25. Oh, we'll run that and look at it again. So here, the mass of, since B was extra big, then it was easier for it to overcome the friction on A. And so you can see that there's still a significant amount of bouncing here. It hasn't quite leveled out after the 6 seconds.